Problem: 1 gram of a non-electrolyte solute dissolved in 50 gram of benzene. So here benzene is solvent and solute is non-electrolyte. That means there will be no dissociation after we dissolve it in solvent. So freezing point lowered by 0.40 Kelvin. So freezing point of benzene is lowered because here benzene is solvent. So as we know that when we add solute to solvent, there is decrease in the freezing point. So that is why now the freezing point of benzene, it is lowered, and it is lowered by 0.4 Kelvin. So the freezing point depression constant of the benzene, that is Kf value, that is given, which is 5.12, and we have to find the molar mass of the solute. Okay, the solute that is unknown, we do not know, but we have to find the molar mass from this information. So here the equation that we will use is difference in the freezing point, that is before and after, that is del Tf, and that is equal to Kf, which is freezing point depression constant, or another name is cryoscopic constant, into molality. So here del Tf is known, Kf is known, but M is unknown. So M will be equal to del Tf divided by Kf, and del Tf is 0.4 and Kf value is 5.12. So from this we can get the molality, which is 0.078. So this is the value of M. Okay. Now according to the definition of molality, what we know, number of moles of solute which is present in 1 kg of solvent. So that means we can say now that 1000 gram or 1 kg solvent, in this case it is benzene, it contains 0.0078 moles of solute. Okay, but the amount of solvent present mentioned here is 50 gram. So we will find out that in 50 gram of solvent what will be the number of moles of solute. Okay, so why we are doing this? Because only in 50 gram of benzene we know what is the weight of solute. Okay, so that is why first we have to find out what is the number of moles of solute present in 50 gram of benzene. Then only we can find the molar mass. So 50 gram solvent, it will contain 0.078 divided by 1000 multiplied by 50 moles, and this is equal to 0.0039. So this is the number of moles that is present in 50 gram of solvent. Now we know that number of moles, that is equal to number of moles, suppose small n, that is equal to given weight, that is W divided by molecular weight. Now here N is known, W is known, but M is not known, and we have to find out M. So M will be equal to W by N, and W is 1 gram, and number of moles we have just calculated 0.0039. So this will be equal to 256.4 gram. So this is the mass of the solute, that is molar mass or molecular weight. Okay. Next problem: 1000 gram of sucrose solution in water. So sucrose is the solute, water is solvent. It is cooled to minus 0.5 degrees centigrade. We know normal freezing point of water is 0 degree, but it is cooled minus 0.5 degree. So obviously now some ice would be separated. So how much of ice would be separated out at this temperature, that we have to find out, but some other information is also given. If the solution started to freeze at 0.38, that means this is the depression in freezing point. That is, normal water is 0 degree centigrade freezing point, but when we are adding the solute sucrose, now the freezing point is lowered from 0 to minus 0.38 degrees centigrade. But we are decreasing the temperature further below. Okay, So that is why some amount of ice would be separated, and what is the weight of that ice, that we have to find out. Express your answer in gram. Kf value is given 1.86. okay, even if it is not given, it is better you remember the value. So Kf for H2O, it is 1.86, because most of the problems you will find where solvent is water, so it is better if you can remember it. Okay, so first of all we need to find out what is the molecular weight of sucrose, and for that we have to know what is the formula. So formula is C12H22O11. so molecular weight will be 12 for carbon, 12 into 12. For hydrogen it is 22 into 1, and for oxygen it is 11 into 16. So this will be equal to 342. So this is the molecular weight of sucrose. Okay, now here we will solve this problem slightly different way, okay, that we have not done before, because if we do this in this way, then it will be easier. So what we will do, suppose here W1 is the weight of solvent, W2 weight of solute. Okay, so number of moles of solute, that will be given mass divided by molecular weight. Given mass is W2, molecular weight 342, that we have just calculated. Okay, so here W1 gram of solvent, that will contain, W1 gram solvent contains W2 divided by 342 moles of sucrose. So if this is the case, then 1000 gram of solvent, that will contain W2 divided by 342 into W1 multiplied by 1000. So this is actually the molality. So now what we will do, in the expression of del TF equal to Kf into M, del TF equal to Kf into molality. So in place of small m, now we will put this W2 into 1000 multiplied by 342 W1. Okay, so that directly we can get the value of W2 and W1, because both are unknown. Okay, so here it is 0.38. Negative sign we will ignore, because we just need what is the difference between the two freezing point values, not the sign. K value given 1.86. In place of molality we will write W2000 divided by 342 into W1. So from this we can get the ratio of W2 divided by W1, which will be equal to 0.07. So suppose this is equation number 1, and here also given that 1000 gram of solution, that means the weight of the solution is 1000 gram. Now what it means, that W1 plus W2, that is weight of solvent, weight of solute, that will be equal to 1000 gram. So now this is equation number 2. So from equation number 1 we can write W2, in place of W2 we will write 0.07 W1, so that we can get the value of W1. So it will be 1000 divided by 1.07, okay, and that is equal to 934.6 gram. So now we know what is the weight of solvent, so we can easily find out what will be the weight of W2. So W2 will be equal to 1000 minus 934.6, which is equal to 65.4 gram. Okay, so when we are that is, there is depression of freezing point, that is minus 0.38, then the corresponding molality is this, and in this molality the weight of solute is 65.4 and weight of solvent is this. Now when we are further decreasing the temperature, there will be some amount of water which will be coming out as ice, because there is a capacity. So when it will over capacity, it will be, that is, capacity amount of water is extra compared to the maximum amount, then obviously some water will be separated and in the form of ice, because temperature is very low. So now what we will do, we will use this equation again, but now in place of W1 we will not write the value of W1 because we need the value of W1. So del TF equal to Kf into M. In place of del TF now we will write 0.5, and in place of Kf it is 1.86 just as before. And now this expression we will write again, but we will write 65.4 multiplied by 1000. So what we have done, we have written the value of W2, but we will not write the value of W1. Let it remain as W1. So W1 basically is the final, that is, to reach the final answer we require what is the value of W1. Now W1 in this case, that is when we are keeping all the things same, only now del TF is 0.5. So under this condition the value of W1 will be 711.4 gram. Okay, so this is the weight of solvent when there is depression in freezing point 0.38. This is the weight of solvent when there is depression of it is not actually depression of freezing point. We are decreasing the temperature from 0.5. So 0.5, that is the extra amount of temperature that we have decreased. So now that is we have to find out what will be the how much ice would be separated. So the ice that will be separated, that is the answer will be W, better we write it W1 prime because we have already used W1. Okay, so the ice that will be separated, the value will be W1 minus W1 prime, that is 934.6 minus 711.4, and this will be equal to 223.2 gram. Okay, so whenever this type of problem you are getting, that is how much of ice will be separated, then better we do the problem in this way, that is in place of molality we can directly put this formula. Okay, now we have reached the last colligative property, which is osmosis and osmotic pressure. So total 4 colligative properties are there. The first we have discussed lowering of vapor pressure, then elevation of boiling point, freezing point depression, and the fourth is osmosis and osmotic pressure. Okay, so here if you look at the jar, here we have a semi-permeable membrane, which is this dotted line. Now what is semi-permeable membrane? It is a barrier that will only allow some molecules to pass through the pores, that is it has some pores, and through the pores only some molecules can pass, and it can block the passage of other molecules. So depending on the size of these pores, some molecules, that is which are smaller in size, that can pass, but comparatively larger size molecules that will not be able to pass. That is the role of semi-permeable membrane. So here we have taken semi-permeable membrane, that is SPM, and the left hand side we have only water molecule. Okay, and in the right hand side we have sugar molecules also, sugar molecule as well as water molecule. That means this side we have solvent and this side we have solution. That means here concentration is high. So when we are separating solvent, pure solvent and solution with some solute through SPM, then what will happen? Water molecules from this low concentration region, it will go towards high concentration region. But the opposite case, that will not take place. That is, sugar molecules cannot come from this side to this side. That is not possible. So only water can pass through the pores of semi-permeable membrane from left hand side to right hand side. So this phenomena of passage of pure solvent from a region of lower concentration, because this is lower concentration, this is higher concentration, okay, to region of its higher concentration through a semi-permeable membrane, this process is known as osmosis, okay. And the flow, how long it will continue? It will continue till the equilibrium is reached, okay. So after one time will be reached when the water molecules, that is the height of the solvent, that will be higher in the right hand side, because water, some amount of water now passed through the semi-permeable membrane from the left hand side to right hand side, okay. Now this flow, that is, it is a natural process, that is spontaneously it is going from left hand side to right hand side, from low concentration to high concentration. But suppose if we want to stop this process, so obviously we have to put some extra pressure on the solution side. So in this side we have to push some extra pressure so that we can stop this movement, okay. So this extra pressure that we have to apply on the solution side, that extra pressure is actually the osmotic pressure. So the process is osmosis, and the extra pressure that we have to put so that we can stop this process, that is known as osmotic pressure. So the pressure that just stops the flow of the solvent, it is called osmotic pressure of the solution. So you can say that the extra pressure that we have to put is osmotic pressure, or you can say that the pressure that just stops the flow of solvent is osmotic pressure of the solution. Another way we can also say that it is the excess pressure which must be applied to solution side so that we can prevent the flow of solvent into the solution side through SPM, okay. So once osmosis is complete, the pressure exerted by the solution and the solvent on the semi-permeable membrane, now it will be same. So once equilibrium is reached, okay, that is osmosis is complete, now the force that will be developed to SPM, that is the permeable membrane, from the solvent side and from the solution side, both will be same, because now equilibrium is reached. But unless there is difference in pressure both side, the osmosis process that will continue. But when pressure is equal both side, then the process will stop, okay. So here from this picture, the idea will be more clear. So initial state, there is semi-permeable membrane. So here we have pure water, and this side we have solution. Suppose it is a glucose solution. So water will flow in this direction, not in this direction, okay. And at equilibrium, osmotic pressure, that is now the level of water in the right hand side, that will increase, okay. Next, if we apply pressure now on this side, that is right hand side, now we can make the height equal again. So to make the height equal, we have to put some external extra pressure, otherwise there will be always a difference in that is, this height difference will always be there. But if we want to remove that, we have to apply some extra pressure, and that pressure is actually osmotic pressure. So when you have taken initially in this state, it will be same, but it will not remain at the same height for a long time, because once water molecules will start to move from the solvent side towards the solution side, then the level of water that will rise, okay, and equilibrium will be reached. So equilibrium will be reached when both side pressure is same. Now to decrease the height again, we have to put some pressure, and that pressure is known as osmotic pressure, which is denoted by the sign pi. So this is pi. Now the equation that we use here is known as Van der Waals equation for dilute solution. Remember, this is for dilute solution. Actually, all the colligative properties that we have discussed only for dilute solutions, because only when it is dilute it will follow the Raoult. Okay, so here we have equation pi v equal to nRT. Now this equation, it is just the analog of the equation which we use for ideal gases, that is PV equal to nRT, where n is the number of moles, R is universal gas constant, T is absolute temperature, P pressure, V volume. So here in place of P we have pi, because now the term is different, which is osmotic pressure. So pi is osmotic pressure. So this equation is very important. So we can solve numericals by this formula. Okay. Now this formula, from this formula we can get some other formulas also that we will see in the next slide. So suppose W gram of solute which is having molar mass M, that is present in the solution. So what will be the number of moles? Number of moles will be given mass divided by molecular weight, that is W by M. Now in this equation, in place of N, we can write W by M. Now when we are writing W by M, now the equation, that is if we want to find out what is the molecular weight of the solute, we can keep here M in the left hand side, and in the right hand side we will have WRT by V pi. Now W by V, that is also density, because density is mass by volume, so we can also write dRT by M. So measurement of osmotic pressure, it provides us the method for determination of molar masses of the solute. So if all these things are known, that is weight, R is constant, T if it is given, volume and osmotic pressure. So if all these things are given, then we can easily find out what is the mass of the solute. Okay, if the solute is unknown. So this is the utility of this colligative property, that is osmotic pressure. Next, this colligative property, that is the fourth colligative property, it has some advantages if we compare with the other three colligative properties, that is lowering of vapor pressure, elevation of boiling point, freezing point, depression. So what are those as advantages? Here, first point, pressure measurement is around the room temperature. So we don't have to increase or decrease the temperature. That is not required, because the whole process can be done at room temperature. Another thing is that here, if we write this equation in this way, that is pi equal to N by V RT. Okay, so N by V means what? Concentration, number of moles per unit volume. So in place of N by V, we can write CRT, or you can write MRT. So M I have already used here, so that is why I am written CRT. So C is basically here molarity, because it is number of moles per unit volume. It is not weight, it is moles by volume, so it is molarity. So unlike other colligative properties where we have used molality, but now we are using molarity. So we don't need the weight of the solvent. If we know what is the volume of solution, that is fine, because this V is volume of solution. So separately we don't have to find out what is the weight of solvent. That is not required. This is another advantage. As compared to other colligative properties, its magnitude is large even when even for very dilute solution. So what happens if the magnitude is very large? Handling of this number will be very easier process if we consider practical purposes. Fine. This method is widely used to determine molar masses of biomolecules, that is proteins, polymers and other macromolecules. Okay, we know that biomolecules they have very high molecular weight. Okay, and biomolecules, they have some issues, that is they are not very stable at high temperature. So if you can measure their molar mass at room temperature, obviously that is better, because higher temperature they may decompose. So that is why, because you know protein is very sensitive to heat. Okay, so room temperature, if there is any process available for the measurement of their molar mass, that is very good. So as this process can be performed at room temperature, so that is why this technique is particularly useful for the molar mass determination of biomolecules. And another problem is especially for polymers, they have poor solubility. Okay, so solubility problem that can also be overcome. So these are the advantages of osmotic pressure over other methods. Okay. Next we have a problem. Insulin is dissolved in a suitable solvent. So see, we have taken biomolecule. So this problem is regarding osmotic pressure, and now you can understand how we can calculate the molecular mass of biomolecules. So its osmotic pressure pi is given in atmosphere unit, in atmosphere of solutions of various concentration. So see, the concentration is given in gram per centimeter cube unit. Be very careful about the units, okay, otherwise there will be error in spite you are doing all the calculations correctly. It is measured at 27 degrees centigrade. Now the slope of the plot pi against C, that is pi versus C, if we draw the plot, the corresponding slope is found to be 4.1 10 to the power minus 3 atm centimeter cube per gram. So what will be the molecular mass of insulin, that we have to find out. Okay, so here which equation we will use? We will use pi v equal to nRT. Okay, now in place of n we can write W by m, that is molecular weight, into RT, or we can write pi W by V RT by M. So what we are trying to do, we are trying to write the expression in such a way so that we can get the equation for pi versus C plot. So for pi versus C, basically it will be y equal to mx plus constant, suppose it is k. So here y is pi, x is c, m is slope. Basically there is no constant because it is straight line equation, but it is that type of straight line where it is y equal to mx, that is it will go through origin. Okay, there is no intersect, so k will not be there. So y is pi, that is in y axis we will take pi, and in the x axis we will take c. So suppose the graph is like that, then here the slope, that is actually m, pi versus c. Okay, now another thing which is to some extent different in this problem is that here concentration is given in gram per centimeter cube unit. Normally what we see that concentration is given moles per unit volume, but here it is given in weight per unit volume. So that is why we have removed n, and in place of n we have written it as W by V, that is weight per unit volume, so that in place of W by V we can put C. So now the equation will be pi equal to C RT by M. Fine. Now the next important thing is here R, it will be used in liter atmosphere unit, liter atmosphere per Kelvin per mole. Okay, so when it is liter, that means it is dm cube, decimeter cube, but here C is given in centimeter cube, so we have to convert it to decimeter. So if C is the concentration, that is in gram per centimeter cube, then per decimeter cube obviously the value will be high and it will be 1000 times higher. So that is why the equation will change to 10 to the power 3 multiplied by C, then RT by M. Now this equation you can compare with mx, y equal to mx. Okay, so here this total quantity will be m. This is x, this is y. Okay, so now we can write that m is equal to, because m value is given, slope is given 4.1, 10 to the power minus 3. So now we can write 4.1 into 10 to the power minus 3, that will be equal to this quantity 10 to the power 3 multiplied by RT by m. Now we will put all the values. R value 0.082 universal gas constant, temperature is 27, we will convert it to Kelvin, so it will be basically 300 Kelvin. So 300 Kelvin and divided by the molecular weight. Okay, so molecular weight is the unknown value that we have to actually find out, the molecular mass of insulin. So m will be equal to 10 to the power 3, 0.082 multiplied by 300 divided by 4.1 into 10 to the power minus 3. So 10 to the power 3 and 10 to the power minus 3 together, it will be 10 to the power 6, and 0.082 into 300 divided by 4.1, it will be 6. So the weight is 6 into 10 to the power 6. So it is matching with which option? It is matching with option C, 6 into 10 to the power 6. So you can see from the value that as it is biomolecule, its mass is very high, it is very large number. Okay, so that is suppose if options are not given, if it is integer type of question, then from the value you can get some qualitative idea that yes, it is very high. Suppose the molecular mass of insulin is asked here and you are getting value which is 100, 200 like that, so that means there is something wrong. Okay, the value must be very high. So this is an indication that you are doing the calculations in a proper way. Fine. Another osmotic pressure problem, but now we do not have any options. It is an integer type of question. So we have to calculate osmotic pressure at 25 degrees centigrade of a solution that contains 1 gram glucose and 1 gram sucrose. So we have two different types of solute, and solvent is 1 liter. The solution volume is 1 liter. Now if it were not known that the solute was a mixture of glucose and sucrose, suppose we do not know that there are two types of solute present in the solution, under that condition what will be the molecular weight of the solute? Suppose it is a single solute. Suppose we do not know what there is two types of solute. If it is single solute, then what will be the corresponding calculated osmotic pressure? That is the question. So here how we will start? We will find out what is the number of moles of glucose as well as sucrose. Now sucrose, its molecular weight we have already seen in other problem that it is 342. But what will be the molecular weight of glucose? Glucose having formula C6H12O6. So its molecular weight will be 6 into 12 plus 12 into 1 plus 16 into 6. So this will be 180. So this is the molecular weight of glucose. So moles of glucose suppose it is N1, so it will be given weight which is 1 gram divided by its molecular weight 0.0056. Moles of sucrose N2, 1 divided by 342, and this is equal to 0.0029. Now total moles N1 plus N2, and that is equal to, suppose it is N, 0.0085. Okay. Now here volume is given, volume of the solution given 1 liter. So if we use the equation pi V equal to nRT, so this is the N which is actually the total number of moles, V is 1, pi that we have to find out. Okay, so pi equal to nRT by V. So this is 0.0085 multiplied by 0.082, that is R value, multiplied by 25 degrees centigrade, which is actually, just add with it 273, it will be 298. So this is 0.208 atmosphere. The values may change it depending on after decimal how many digits you are taking. It may be 207 or 208, but more or less it will be same answer. Okay, so now we know what is the pi value, that is what is the osmotic pressure, by adding the number of moles individually for glucose and sucrose. Okay, now we have to find out as if there is only one solute is present. Okay, actually it is not present, but we are considering it in that way because question is given in that way, that is molecular weight of the solute corresponding to the calculated osmotic pressure. So again we will write the same equation, but in place of n, now we will write mass by, as that is given mass divided by molecular weight into RT. Okay, so m is basically unknown that we have to find out, so we can write m is equal to WRT divided by pi V. So V is 1 and pi we have calculated 0.208, and weight, in place of weight what we will write, 1 gram of glucose, 1 gram of sucrose, so it will be 2 gram. So 2 into 0.082, same temperature, divided by 0.208 and 1 liter. So directly we are putting in liter because universal gas constant, that is in liter atmosphere unit, and this will be equal to, which is almost equal to 235. Okay, so see the value, if you compare with the molecular weight of glucose and sucrose, that is 180 and 342, this value is as if intermediate of these two. Okay, so this is the answer. Now we know what is osmosis, but what is reverse osmosis? So from the name we can understand that now the movement of the particles, it will be from higher concentration to lower concentration, because in normal osmosis we have seen that water molecules are moving from solvent, that is pure solvent, towards solution. But in reverse osmosis, in short it is known RO, that is the direction will be opposite. So direction of osmosis can be reversed if a pressure greater than the osmotic pressure is applied to the solution. So in the definition of osmotic pressure, what we have seen, that is the excess pressure that we have to apply to just stop the process. So you are stopping the process, but if you are giving some excess pressure, that is excess that of the osmotic pressure, then what will happen? Now there will be some movement, because osmotic pressure is that pressure which is just enough to stop the process. But when it is more than that, now there will be movement of solvent particles. So these are the water molecules and these are the sucrose molecules. Okay, sorry, it is salt water, so it is NaCl particles. So if these are the solute particles, so in this side it is basically solution side and this is solvent pure. So now this is SPM, that is semi-permeable membrane. So now through the pores only water molecules are passing and the movement is from solution towards solvent, and that is possible only when you apply some pressure, and remember it must be greater than osmotic pressure. Otherwise the process will just, if you apply only osmotic pressure, the process will just be stopped but the opposite movement will not take place. But if you are giving excess pressure compared to osmotic pressure, now there will be movement of particles, that is solvent particles, from solution side to solvent side. So this phenomena is called reverse osmosis, or in short RO. Okay, and very important application is that this process is used for desalination of seawater. We know in seawater there is NaCl present with the water. So from the seawater, which is basically solution, if we want to get pure water, then obviously normal osmosis will be of no use. Okay, now we need the reverse osmosis, and osmosis is natural process, but reverse osmosis, it is not natural. We have to put some extra pressure. Okay, so by this process, reverse osmosis, what will happen, from this side water molecules will come towards pure solvent side. So as a result, we will get desalinated water, because NaCl water is known as saline water. So desalination means now we are removing the NaCl from the water. So this is desalination of seawater. This is very important application of reverse osmosis. Okay. Next is tonicity and osmosis. So this is completely a new term. Mostly it has application in biology, but you can get numericals regarding this terminologies. So here these three terminologies are very important, and these three are hypertonic, isotonic, and hypotonic. Okay, so it is known as tonicity, and it has some relation with osmosis. So suppose we have isotonic solution. So what is isotonic solution? It has same osmotic pressure at a given temperature, that is for two solution. If they are having same osmotic pressure, they will be called as isotonic. So suppose here we have taken red blood cell, and inside the blood cell there is 0.9% NaCl solution. Okay, and outside it, that is outside and inside, both are having similar type of fluid. So osmotic pressure associated with the fluid which is inside the blood cell, that is actually equivalent to this 0.9% M by V. That means it is same in NaCl solution. Actually inside, I have said that by mistake, that is inside there is no NaCl solution, but the osmotic pressure inside the cell, that is similar as that of 0.9% M by V NaCl solution, which is saline water. So that is why if this solution is injected intravenously, there is no problem, and this is done. Okay, so when this type of solutions, we are separating them by SPM, semi-permeable membrane, no osmosis will take place, because that is not required. Both sides is same osmotic pressure, so why osmosis will take place? Okay, now the next process, hypertonic. Solution having higher osmotic pressure than that of another solution, that is known as hypertonic. Now again same cells we have taken, and we have kept them in 0.9% NaCl water, that which is more concentrated compared to 0.9% NaCl water, because only 0.9% M by V NaCl water is having equivalent type of osmotic pressure. But if you are now keeping them in higher concentration compared to this value, then what will happen? Now water will flow out of the cell, because when it is osmosis process, what we know, water molecules or solvent molecules, they always move from concentrated side towards a low concentration. They move from low concentration side to higher concentration side. So now inside the cell, that is hypertonic, inside the cell the concentration is high. Here concentration low, and outside concentration is high. So water molecule inside the cell, it will move outside. So see from this picture, water molecules are going outside. That means the cell will shrink in size. Okay, and the opposite process, that is, now we are keeping the cells in low concentration solution. So what will happen now? Solution having lower osmotic pressure than that of another solution is known as hypotonic. So if we are keeping these cells in solution which is less than 0.9%, now what will happen? From outside, now water molecules will go inside. So water, these cells, they will swell, size will be bigger, and if the process is going on, one time will be reached when there will be, that is, the cell will burst. You can see here the cell is burst. Okay, so three types of concentration terms here we have: isotonic, hypertonic and hypotonic. So in numerical it is very common that it will be given as mentioning isotonic solution. So suppose if it is said that you one solution is given which is isotonic with another solvent, okay, that means if you know the concentration of this another solvent, then you can easily understand what is the concentration of the other solvent. Because though we are saying here that is the definition is in terms of osmotic pressure, that is same osmotic pressure, but remember it is mostly, you can also say in another way that isotonic solution, they are actually having same concentration, because we know that osmotic pressure is equal to CRT, concentration into RT. Now these two are constant, so pi is directly proportional to C. That means if pi is equal, that means C will also be equal. Okay, because it is directly proportional. So here we have a problem which is regarding tonicity. So 0.6% weight by volume urea solution, it will be isotonic with which of these solution? That means here concentration is represented by weight by volume. Concentration can be represented by different ways. Okay, molarity, molality, weight by weight, weight by volume, ppm, etc. So here weight by volume in that representation is such that it is given in weight per volume. That means 0.6 gram urea is present in 100 ml solution. Okay, but all this concentration, that is in option A and B, it is given in molarity, and in option C and D it is given in W by V. Okay, so we will find out that it will be isotonic with which of this solution. And remember it, if we express it in molarity, then only we can compare with these two, because in pi equal to CRT, in that expression the concentration is expressed in molarity. So whenever we are trying to compare isotonic, whether two solutions are isotonic or not, we have to express it in molarity. Okay, then only we can compare, because in this equation pi equal to CRT, we express concentration in molarity. So first of all we have to know, if we want to convert it to molarity, what is the molecular weight of urea, and for that we have to know what is the formula of urea. So urea is H2N CO NH2. That means the formula will be CON2H4. So molecular weight for C it is 12 into 1, for oxygen 16 into 1, for nitrogen 14 into 2, and for hydrogen it is 1 into 4. So if we add it, it will be 60. This is the molecular weight of urea. Okay, so now we can say that 100 ml solution contains 0.6 gram urea. Okay, but for molarity we need to know that in 1 liter, that is 1000 ml solution, what will be the number of moles. but here we are calculating it in terms of gram, but later we can convert it to moles. So 100 ml solution contains 0.6 gram urea. So 1000 ml solution will contain, it is actually 6, but the calculation will be like this. So it is 6 gram. Now this is the given weight, so we will convert it to molarity. That is, for that we will convert it to number of moles. So number of moles N is given weight divided by M. So given weight is 6 and molecular weight is 60. So this is equal to 1 by 10. That means it is 0.1. This is the molarity. So 0.6 gram W by urea solution, it will be isotonic with, it is matching with which option? 0.1 molar. It is not important which solute is present because it is colligative property. So it is only the number of particles important. Okay. So 0.1 molarity, that is matching with this glucose solution. Okay. Now don't think that this is 0.6% W by V, this is also 0.6% W by V. So this will be the answer, but not, because here it is expressed in molarity. So we have to first convert it to molarity, then we will compare. So 0.6 molarity glucose solution, this is the correct answer, that is option A. Okay. Now we know colligative properties, but there is another term which is abnormal colligative properties. So what is abnormal colligative properties? We know that we can determine molecular masses of the solute with the help of colligative properties. So from osmotic pressure, how to calculate it, we have just seen that. But for other colligative properties, suppose lowering of vapor pressure, elevation of boiling point, freezing point, in lowering of vapor pressure you can calculate mole fraction, and if you know the mole fraction and number of moles or given weight of the solute, you can easily find out the molar mass of solute. Similarly, we can know molality from elevation of boiling point and depression of freezing point, because del TF and del TB, that is equal to K for KB in multiplied by molality. So if we know the molality and given weight of the solute, that is known, we can easily find out molar mass. So molecular masses of the solute can be easily find out with the help of colligative properties. But this is possible only under some assumption. If these assumptions are maintained, then only we can do it. So what are those assumptions? First of all, the solution is dilute, that is solvent is available in large amount so that it can obey Raoult's law. And the next important thing, the solute neither when dissociation or association in the solution, because it is colligative property, it is dependent on the number of particles of the solute, not on the nature of the solute. So if the particle is undergoing dissociation or association, that means when that is before putting the solute in the solution, there is no dissociation or association. So now the number of particles, and when you have added it to solvent, after dissolving it, the number of particles, that will decrease or increase. So it will decrease if there is association, but it will increase if there is dissociation. Okay, so that is the problem. So if this type of things are going on, then the result that we will get, that will be wrong, and this is abnormal colligative property. So mainly here we will focus on these two things, that is dissociation and association. When this will go on, what we will do, because when there is dissociation association, we cannot get the correct value. So there must be some other ways so that we can remove this problem. Okay. So how do we determine the molecular mass of solute in case of the above assumptions are not valid, especially the second point, that is dissociation or association. So suppose if it is non-electrolyte, it is fine, but if it is electrolyte, that means it will dissociate. Then what we will do? Since colligative properties depend upon the number of particles of the solute, this abnormality, it is because of the association or dissociation of the solute particles. Okay. So when there is association, what happens? We will try to see by taking example of acetic acid. So two molecules of acetic acid, if you put it in benzene solution, there will be dimerization. So this is known as association, and this is, you can see the dimer here. So in case of association, there are less number of solute particles. So initially there is 2, but after dissolving it, it is 1. So there is decrease in number of solute particles in the solution, right? Colligative properties also decrease along with the solute particles. So it is, colligative properties are directly proportional to solute particles number. So if solute particles numbers are decreasing, that means colligative property value that you will find, that will also be wrong, and it will be lesser than the actual value. Colligative properties are inversely proportional to the molecular mass of solute. Okay, so that you can easily understand from the expression of pi equal to CRT, because in place of pi v equal to nRT. Okay, n is W by M. So pi v equal to W by mRT. That means pi is inversely proportional to M. Okay, and you can also suppose if you consider this equation, it is Kf into molality. Now molality is actually mass, given mass divided by molecular weight. That means delta F is inversely proportional. So in all the cases you will see that colligative properties are inversely proportional to the molecular mass of the solid. So the unknown mass, molar mass, that is if the solute is unknown, if you find the molecular weight, that will be higher than the actual weight. Okay, you can also understand it from this expression. That is now, that is when it is acetic acid, it is a molecular weight of CH3COOH. But as if now it is behaving as if it is a single molecule, and this molecule has higher atomic weight, higher molecular weight, which is clear from this, it will be double. So that is why when there is association, the molar mass that you are calculating, you will get higher value compared to the actual value. So this is the problem we will face in if there is association. Now what about dissociation? So if there is dissociation, normally you will see it in case of electrolytes. So there will be higher number of solute particles in the solution. So here we have example KCl, before it was 1, but after it was 2, K plus and Cl minus. So colligative properties will, it will increase, not decrease. Okay, and colligative properties are inversely proportional. So that is why now the mass that you will get, that will be lower than the actual mass. In the previous case we have seen the value of molar mass that we are getting, that is higher than the actual value. But now we are getting lower value compared to the actual value. So this is the problem we face in dissociation. So to remove the problem, there is one factor which we introduce, is known as Van der factor. So to sort out this association dissociation problem, when we calculate the molar mass of the solute or the colligative property, not always molar mass, then we have to introduce this I factor. So what is I? I can be expressed in any of these expression. Okay, so normal molar mass, that is the actual molar mass, divided by the molar mass that we are getting, that is experimental. Okay, so actual and experimental, there will be some difference. Fine. So if suppose it is dissociation, the actual, if it is x, then initially it is 2x. So in that case I will be equal to half. Okay, that is now this factor, it may be fraction also, it may be greater than 1 also. And we can also express it as if it is observed colligative property divided by calculated colligative property, or total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. So if you take the example of KCl, it will be 2, that is total number of moles of particles after association or dissociation. So in this case it will be dissociation, so it will be 2, and number of moles of particles before association and dissociation, that will be 1, so it will be 2 by 1. sorry, here one mistake I have done, that is it is actual and experimental, that is fine, but actual, that is in case of dissociation we get lower mass, that means experimentally the mass that you are getting, that is x, so it is x, it is 2x and divided by x, so it will be 2. Okay, so in this case, that is in case of KCl, the I value you can find by using any of this expression. Okay, so it depends on the numerical, what type of information is given. Depending on that, we have to use any of this equation. Okay, now we will see some values of Van der factor. So here we have concentration, different concentration of this solution. Now sucrose is non-electrolyte, temperature is constant, sucrose is non-electrolyte, so whatever concentration you take, it doesn't matter because it will always be 1. We know that for electrolytes, that is NaCl, K2SO4, MgSO4, when you dilute the solution, there is increase in dissociation. Okay, so that is why you will see that with decrease in concentration, the value of I is changing, it is increasing. Okay, and the expected value is 1, obviously because it will not dissociate, and in case of NaCl it is 2, in case of K2SO4 you will get 2 potassium ion, 1 sulfate, so it is 3. In case of magnesium sulfate, 1 magnesium ion, 1 sulfate ion, so it is 2. Okay, so when as we know that it is colligative properties are for dilute solutions, so when it is dilute solution, now you can see that the values, that is the number of particles after dissociation, it is very close to the expected value, 2.32, then 2.7, then 2.8. So this is most close, that means now there is complete dissociation, so that is why it is close to the actual value, because theoretically we should get 3 particles, but you will get lesser value if it is concentrated, because all the K2SO4 will not dissociate it to potassium and sulfate. But when it is very dilute solution, 0.001 molarity, now there will be complete dissociation and the value will be matching with the expected value. Okay, so this is the table from which we can understand how it is changing with concentration, and when concentration is very low, it is matching with expected value. And how we can include the Van der factor? So here we have 4 colligative properties. These are the expression. This is lowering of vapor pressure, this is mole fraction of solute. So this is the normal case, but when there will be dissociation or association, we have to multiply this. Okay, so in each case, del T be equal to Kb into M, del Tf Kf into M, but now we have added I. So here the colligative property that we will get when there is association or dissociation, we can get the actual value, that is the value that is actually correct, only after we multiply this I. Okay, so in all these equations, it is very simple, we have just multiplied this I in each case, that is the difference. So this value of I, it will be 1 when it is non-electrolyte. So if there is no dissociation or association, suppose you have taken sucrose, so obviously this equation is fine, then no need to include Van der factor. But when there will be dissociation or association, we have to include the Van der factor, otherwise we will not get correct result, whether it is molecular mass or any colligative property.